Hello, I think we kick off. My name's Darren Lombroso. I'm going to be chairing this meeting. I can see we've got just over 70 people joining. So welcome to this Chartered Institution of Water and Environmental Management Central Southern Branch meeting on agent-based modelling for juvenile eel migration through estuaries. And just before we kick off the talk, just a few housekeeping issues. So if you could keep your microphone on mute throughout the webinar. The webinar is being recorded. It will hopefully, providing there's no copyright issues, be appearing on the SciWM website at some point in the future. If you look at the bottom of the screen, you'll see that there's a Q&A and a chat box. If you have any technical issues, then please put the issue in the chat box, and we've got Jane and Barbara here from SciWM who will help you out if you have any technical issues. We'll be taking, or Tom will be taking questions, the presenter, at the end of the presentation. So if you could put those in the Q&A box, and then I will read those out to Tom for him to answer at the end. This is attributable for continuing professional development, but SciWM don't produce certificates, so you can put this down as continuing professional development. So most of our talks, most of SciWM's talks are virtual. So just to give you an update on what's coming up, SciWM have got an international event on the 14th of April at the Floods and Coast Conference, which is a session on broadening innovative investment in flood and coastal erosion risk management. That's £25 plus VAT. And then in terms of branch events, on the 4th of March, that's a week today, there's an event by the SciWM Rivers and Coastal Group on modelling the Brumadinho tailings dam failure in Brazil. That happened just over 2 years ago and the loss of life. And then on the 24th of March, there's a webinar on a novel method to estimate the risk to people from floods. So those are branch events coming up. And then in terms of SciWM development and learning, there's been some courses just recently launched by SciWM, and there's one coming up on the 8th of March on leadership to influence urban projects for wellbeing and environmental sustainability. There is a charge for that, that's £175 plus VAT. And then there's another one which hasn't got a date as yet, which is urban wellbeing in practice and how to develop urban projects for wellbeing and environmental sustainability. So Barbara will be putting all those in the chat. There's links to those events all in the chat, but you can also find them online at the SciWM website, which is www.sciwm.org. So under either /training or /events, and you can register for the events now. So that's the general housekeeping. So I will just give a quick intro to Dr. Tom Benson from HR Wallingford. So Tom is a principal researcher at HR Wallingford, which is an independent research and consultancy organisation in the UK. He's got a master's degree in advanced instrumentation systems and a PhD in modelling sediment. And he's spent probably the best part, maybe more, of 15 years at HR Wallingford doing some very clever stuff of modelling sediments, but also modelling fish, as we'll see today. So especially modelling eels, but also how fish react to noise. But I don't really want to talk anymore. I'll hand over to you, Tom, and then we can kick off the presentation.
Thanks, Darren. Brilliant. Thanks for inviting me along to this. I can see we've got over 100 participants now, which is good. So just to kick off, just to point out on this image here, I'm sure some of you will have already noticed this is actually an electric eel. I just want to point out, I'm not talking about electric eels today. I'm talking about European eel. I'm going to be talking about agent-based modelling of juvenile eel migration through estuaries, as Darren has already said. So next slide. I'll just tell you a bit about myself. Darren's already introduced a little bit about me. Throughout my studies and career, I've kind of learned that to understand the marine environment, you really need to understand things using a various range of techniques, which include measurement, modelling, and a bit of imagination. And with all these three things, you can gain better understanding. And you basically you want to have a bit of all these things. You can't just have one of these elements. I started off my career at Bangor University, where I did an ocean science degree, learned all about the marine environment. I then diverted a bit, did a bit of advanced instrumentation systems for a master's, and then I carried on at UCL. I did a PhD in estuarine sediment transport modelling. I then carried on in my work in the marine environment. I got a job at HR Wallingford in 2005, where I've been since. And my main interests and expertise are hydrodynamic and sediment modelling for port development studies. I also do a lot of underwater noise modelling for environmental impact assessments. Probably for the last 8 or so years, I've been looking at agent-based modelling of fish and mammals, which is also used for environmental impact assessment. This talk is mainly about a paper that's just come out. I think there's actually a link to this paper in your notes. The paper is titled Agent-Based Modelling of Juvenile Eel Migration via Tidal Stream Transport, and it's in Ecological Modelling. And you can all have a look at that because it's an open access journal paper. I do need to acknowledge quite a few people. It's a multidisciplinary project, which was titled Vaccinating the Nexus. Sorry. So the Vaccinating the Nexus investigated the resilience and sustainable management of the water and energy food nexus, which is quite a big mouthful, but it's what underpins this whole study. That was led by the University of Southampton. It was funded by the Engineering and Physical Sciences Research Council, and it was in collaboration with a number of people, including HR Wallingford, University of Southampton, University of Nottingham, the EPSRC. Data were also provided by the Zoological Society of London, and we also got models provided by RWE Power and also the Port of London Authority. So, an overview of the talk. So what we're talking about is glass eels, or juvenile eel, which are on the right in this picture. They're small, semi-transparent animals. So the first thing I'm going to do is talk about the background of the research and look at the life cycle of the European eel. I'll then talk about why we want to investigate them. And then I'll talk a little bit about what an agent-based model is and how we can use this method to assess the impacts on juvenile eels. So I'll then describe the new ABM. I'll try not to talk about any maths. If you want to see the maths, it's in the paper. And then I will talk about the application of the model to 2 estuaries. The first estuary will be the Thames estuary in London, in the UK, and there we'll be testing eel behaviours. Basically, we do scenario testing the eel behaviours and compare the data from the model against data provided by the Zoological Society of London. Then I'll be looking at the Milford Waterway, where there's a power station, and we'll be looking at eel entrainment in the cooling water intakes of the gas-fired power station. And then at the end, I'll summarise, and there'll be time for questions, I hope. So let's start off by looking at the life cycle of the European eel. It's fair to say that the life cycle of the European eel is nothing but extraordinary, really. So the eels start off as eggs, which are laid somewhere in the Sargasso Sea. The exact location of the eel eggs is not known, but it's basically the rough area was found in 1922 by Professor Ernst Johann Schmidt. He was Danish, and he found that there was a large concentration of leptocephalus, which are these leaf-shaped larvae of the eel. And basically, these larvae drift on the Gulf Stream about 5,000 miles, and they end up at the European coast. it takes about a year or so for them to get to this area, and by that stage they've turned into glass eels, which are this next stage in their life. And then they decide they want to swim up estuaries, and as they get into brackish water, they then pigment, they turn into slightly browner elvers, they're called, and then they move their way up into the freshwater where they mature into yellow eels. After about 5 to 25 years, they then become complete adults, where they transform into a silver eel. And this is this life stage is basically a swimming machine. What happens is their stomach dissolves, they don't eat anymore, and they just swim all the way back to Sargasso Sea, where they spawn and then die. So that's the life cycle of the eel, which really is quite amazing, to be honest. And what we're actually focusing on in this talk is the upstream estuary migrating stage, which is actually these two stages, which we're going to refer to as just juvenile eel, so the glass eel and the elver. I must say that this diagram is a really nice diagram. I didn't draw it. It was done by Alessandro Cresci, and he's got a wonderful paper on the comprehensive hypothesis on the migration of the European glass eel. So I refer you to that brilliant paper on migration of the eel. Let's have a look at the juvenile eel swimming abilities. There were some measurements done recently at the University of Southampton by Paolo Vessa in 2020, and papers out in 2020. And this video on the left, believe it or not, there's some eels swimming in this video. I don't know how well you can see this, but the whole point is that they're very hard to see. They're small, roughly 10 centimeters long. They're semi-transparent. They also mostly are active in the dark. I think this was actually performed in darkness, and these are infrared lights. So they're very hard to see in the wild, and that's why laboratory experiments are needed to actually work out their swimming capabilities. The results of the experiment showed that they tend to swim in burst and coast mode. Basically, the duration that they actively swim against the current is dependent on the near bed current velocity in this graph, and that's the active swimming time on the left. And so you can see, and also it's dependent on temperature. So basically in water, they prefer slightly warmer water, they'll swim for longer. But if the current gets as much above 0.2 or 0.3 meters per second, they really struggle against the flows. So they're pretty slow swimmers, I think is what we're trying to say from that. Now, the thing is, these eels have to migrate up an estuary. And so since they're slow swimmers, they must adopt some kind of swimming behaviours to help them get up the estuary efficiently. This graph on the right is taken from Harrison et al. 2014, and it shows a theoretical idea of selective tidal stream transport, which is the method by which it's thought that eels swim up estuaries. So at the top is during flood tide, and it's assumed that the eels are dispersed through the water column or possibly nearer the surface, and they take advantage of the flood flows. And also they drift during this stage because they don't need to swim, because the currents will take them with the flow. At high water or early ebb, it's thought that they swim to the margins. Now, the reason why this is thought is because fishermen who fish for eels tend to stand on the banks with poles, and they have nets, and they tend to catch them at the early ebb near to the bank of the estuary. So there's anecdotal evidence there. In the model, we've actually called this behaviour edging, just to point that out. On the ebb tide, because the flows are faster than their swimming speed, they then swim to the bed and they anchor and wait for the flows to reduce, just to prevent them being swept back out to sea again. So why would we want to investigate eels? Well, the reason is the status of the European eel is critically endangered. This is an official declaration of their status by the International Council for the Exploration of the Sea. Now, the Graphs here show the recruitment indices for eels over time since the 1960s. And you can see that since the 1980s, there's been a massive decline in eel numbers. This is glass eels on the left for North Sea and elsewhere in Europe. Compared to the 1960s to 1979 average, there are now only 1% left in the North Sea and only 6% elsewhere in Europe. For yellow eels, which is on the right, it's slightly more, but still a dramatic decline to only 17% since 1960-79 average. So what's causing the decline? Well, there is a number of possible reasons. Of course, overfishing is a very likely culprit, and there is quite strict regulation now on the fishing of eel. Another possibility is obstacles and barriers. There have been many dams and power stations being built in coastal areas. I'm going to talk about that a bit more in a second, because that's what we're focusing on. Other reasons of the decline possibly are pollution, parasites and pathogens, and also climate change. And you may wonder how climate change can actually be impacting them. Well, for many reasons, it could be affecting the Gulf Stream, which is how they drift to Europe. It could be affecting rainfall or river discharge, just in changes to rain patterns. It could be affecting water temperature and also ecology, for instance, predators. In terms of obstacles and barriers, the European Parliament's Committee on Fisheries states the following, and I'll just go through this quickly. The introduction of barriers presents one of the major factors affecting riverine fish populations, in particular for migratory species. With regard to eels, different types of obstacles and barriers, including culverts, weirs, bridge aprons, dams, hydropower stations, pumping stations, tidal flaps, and sluices, can adversely affect their continental life stages during migration. Typical negative effects of barriers include the loss of upstream habitats, which is very important. Basically, the eels can't get to the rivers. Delays in migration, which is important because they have a certain amount of energy to get to where they need to get to. And direct mortality at pumping stations, water intakes, which is actually what we're focusing on this talk today. For the adult silver eels, there's also the added problem of hydropower turbines. So on the downstream migration, they may actually swim through turbines. We're not actually assessing this now, but we are doing some research to look into that. So let's have a look at a little bit more detail at power station cooling water intakes. What's the problem here? Well, clearly since the 1950s, 60s, up until, in fact, the 1990s, there was a huge increase in the amount of power being used globally, including the UK. This graph on the left shows a breakdown of the different kinds of the energy produced by different kinds of power production. The white line is the total, the black line here is coal, the yellow line is oil, and the purple line is nuclear. And as you can see, since the 1960s, there was increases through all of these. And with this kind of energy, you need cooling water. So generally speaking, there was a big increase in the number of intakes that were installed along coasts and estuaries. It's a similar picture around the world. This is just looking at the middle graph is just looking at the nuclear power production. And as you can see, in America, Europe, Asia, there were large increases in the amount of nuclear power. Again, for nuclear power, you need cooling water. So are we sure that intakes actually are a problem? Well, there's a couple of, there's actually quite a lot of literature about impingement and entrainment of fish into intakes. There's just two examples here I'll just quickly mention. There's the Long Gannet coal-fired power station, which was in the 4th estuary in the UK. It's now decommissioned. But in 2000, 57 million fish were impinged on the screens just in 1 year. In Sweden, the Forsmark nuclear power station, 31 million fish were impinged on streams at the intakes in 2010. It was also estimated that 1,300 adult eels per year could be saved using a fish return system. And this is the thing, modern power stations which are being built, they tend to have a fish return system. And so there is activity trying to reduce the number of fish which are being impinged. But the problem with juvenile eel is that they're so small that screens aren't really effective at preventing them from going into the intake or getting damaged when they do so. This is just a picture, and in the bottom right there's a picture of, this is Sizewell. This shows that the intakes and outfalls of power stations are generally located in coastal or estuarine regions. So how do we address this problem? I mean, how do we actually model how many eels might be getting affected by intakes? And what we decided to do was develop an agent-based model. So what is an ABM? Oh, that's the acronym for an agent-based model, obviously. So, well, numerous individuals or agents are placed in an ABM in an environment or framework. And these individuals can be plants, animals, people, vehicles, game characters, you name it. There are a wide variety of agent-based models. And these individuals interact with the environment over time, and also with each other. And that's basically what an agent-based model is. You've got individuals interacting. So sometimes ABMs are spatially explicit, and this is the kind of ABM we're talking about here. And by spatially explicit, I mean the agents are placed in a geometric space, so they're placed in real-world coordinates. The agents can also be mobile or stationary, and this makes this kind of methodology suitable for modeling ecology. Just a nice picture on the right. This is a murmuration of starlings, which I captured in Aberystwyth. And this sort of highlights exactly what we're talking about. We've got numerous individuals. They're interacting with each other and the environment. And from that, you get an emergence of behavior, which is basically, there's a complex pattern to the behavior when you look at the population as a whole, which is the whole point of an agent-based model. So this is one of the main reasons for using an agent-based model, is the emergent behavior you get when you just apply a few simple rules to individuals. On the right here, I've got an example, just a nice video showing what you can do with an agent-based model and why it's useful. So here we've got two types of fish, the yellow and the blue. We've got a shark in there as well, and the shark is going around trying to eat the fish. The fish are identical, other than the blue ones are schooling. And you say, well, okay, what's the point of that? Well, this is quite a long animation, so I'll just forward wind it. What you'll see through time is that the yellow fish are being eaten by the shark more quickly. And you end up with more blue fish than yellow fish. And that just shows how an agent-based model can be used to assess behaviors and how they affect the life of the animals. Agent-based models can also be used for prediction. Here we've got another model. Let's play it. And this model is looking at fish swimming through a turbine. I mean, it's quite a gruesome model, but you know, underwater, this kind of thing does happen. You have fish going through a tidal turbine. There's a probabilistic model whether the fish get hit, and also whether they are likely to be injured or actually killed. So the red ones are being injured, the white ones are being killed, and the white ones tend to be at the tips of the blades. I don't know if you can see, they're actually around the edges. So it's so from this you can actually start predicting effects of perhaps installing tidal turbines. There's actually a paper we did recently down here, which I'll refer to look at that in more detail if you want to. So that gives you an idea of what an agent-based modelling of fish is. Now I'll talk about the actual bits we did to develop the fish behaviour model, the juvenile eel behaviour model, sorry. The underlying Lagrangian fish tracking model, which is what I've just shown you, is called hydroboids. We can couple that to a 3D hydrodynamic model. We did previous studies identifying spawning grounds of European smelt using this model in the Thames estuary. This was a collaboration with ZSL again. We've also done fish and mammal fleeing models for underwater noise impact assessments, and we've used it for larval dispersion studies. So there's a wide range of things you can use this kind of approach for. The new bit of the model, which we're talking about now, is the juvenile eel swim behaviour model, where we've added in behaviour of the eels, which includes the selected tidal stream transport, and also the swim speeds from the University of Southampton. So on the left here, this is quite a big flow diagram. It looks a bit complicated, but this, in a nutshell, is what we developed. So this is the agent-based model. It can get broken down to simplify it. You can look at it in 5 blocks. So you've got, 6 blocks. And you can break that down even further into 2 blocks, which the first 2, which is the initialization of the fish and the position updating, is this Lagrangian Eulerian model, which already existed, which is called hydroboids. This model is a correlated random walk model. And basically what happens is the fish are placed in the model in 3D space. They are then advected by the flows. So the start position was on the bottom left, and they are vectored by the flows. So it pushes the fish downstream, but then the fish also has its own swimming capability, so it has a course made good at the end, which is here. At each time step of the model, so the model is a time stepping model, the eel is repositioned, and it's also included, in the swimming is included a random offset in its heading, which is just there to basically make the simulation more realistic. It adds some randomness to the fish's direction. There's also land avoidance in this, so the fish don't swim out of the model domain or onto dry land. The next part is the eel behaviour part, and essentially all this is trying to do is modify the eel's swimming direction and speed, so that it simulates this selected tidal stream transport, which we've been talking about. So on the right, all we're trying to do is resemble this STST in the model. Now, one thing that was not described in the selected tidal stream transport theory is how the eels know if the tide is flooding or ebbing. So eel are known to perform rheotaxis, as we saw in that video earlier. The eels were swimming against the flow. The thing is, in a tidal situation, the flow changes. So at some point, they must be swimming against the flow. At some point, they must be swimming with the flow. So there must be a switch whereby they decide whether to swim with or against the flow. And for that switch in the model, we've used the salinity gradients. So obviously near the sea, the salinity is higher, and up the river, the salinity is low. Therefore, you've got a gradient of salinity, positive gradient out of the estuary. Now, if the flow is in roughly the opposite direction to this gradient, then clearly it's in the model, it's assumed that it's the flood tide, and the eel aligns itself with the flow vector. Conversely, during the ebb tide, the flow is basically in the same direction as the positive gradient in salinity. Therefore, the eel aligns itself against the flow. And that's it. That's basically how the eel knows that it is flood or ebb tide. Then, following on from this, once it's decided if it's in ebb or flood, in the ebb or flood regime, it performs behaviours. During the ebb tide behaviour, it has two different kinds of behaviours depending on the flow speed. If the flow speed is less than the swim speed of the eels, then the eel swims towards the channel margins, which is that edging behaviour. And it does this by assessing basically the velocity either side of its heading, and it moves towards the slower side. And that way it's been shown, from testing the model, we can clearly see the animals make their way to the edges of the channel. Now, as the ebb tide increases in flow, then the animals struggle to swim against the flow, and what they do is they swim down to the bed. And so we have a threshold of the flow being faster than their swim speed, and then they swim down to the bed, and then they anchor and wait for the flows to reduce again. Note also in the model, we've got this eel behaviour where they perform this downward migration also during the daytime because they want to avoid predators. So we've included this behaviour in the model as well. During the flood tide, as the flows reduce and then they turn round and then they start going in the same direction as the eel's heading, when the flows are less than the speed of the eel, then the eel is modelled to leave the bed and swim upwards. Once the flows increase to beyond the speed of the eel, then in the model, the eels are assumed to drift, i.e. their swim speed is set to 0 and they just drift with the flow. So that is that flow diagram in a nutshell. So that's what we put into a model. Right, so moving on from the theory of the model, let's apply it to two situations. We've got two case studies I briefly want to touch on. So first case study is on the right. It's the Thames estuary in the UK, in London, and then the second case study is the Milford Waterway. Just showing you where they are there. Let's look at the Thames estuary first. So the Thames estuary is the second longest river in the United Kingdom at 346 kilometres. It has a catchment area of 16,000 kilometres squared. The tidal limit is at Teddington Lock, which is 112 kilometres from the mouth. Fortunately, we have at HR Wallingford, we have a Telemet 3D hydrodynamic model, which is a 3D model with salinity in it. This was developed at HR Wallingford for the Port of London Authority, who kindly let us use it without any license fee. In addition, we're lucky enough that the Zoological Society of London gave us some eel trap data, and the data were collected in 2014 at Stony Sluice, which is on the River Brent, which is off the Brentford Creek, which is quite far up the Thames. I'll show you on that in a minute. So this image on the top right is actually the eel trap. It's like an eel pass, and the eels swim up that to go over the sluice. And in this case, they fall into a trap, and every few days people come along and collect them to count them. And the graph on the bottom right shows you the numbers captured. The thing to note is that it tends to happen in peaks and troughs, which is what we're trying to model. Right, so quite a busy slide. This in the top right here, we've got the model of the Thames. We have an eel release area here, which is a bit up from the model domain boundary, downstream boundary. It's actually around the Gateway Port area. So we release the eels in here. We release them at 12 agents per hour, so just over time, for a full period of about 5 months, which is the period over which measurements were collected. So the period was between the 18th of April and the 30th of September 2014. And as the eels swim up, there's a bit of a zoomed in portion here. You see Brentford Creek, and if you zoom in further, you can see Stony Sluice, which is where they were counted. In the model, because this area isn't hugely resolved, what we do is we actually count the agents in a region close to Stony Sluice. And the model setup, just briefly go through this, the time step of the model was 30 seconds. The average swim speed of the eels was 0.2 meters per second with a standard deviation of 5 centimeters per second across the population. Had a small persistence error of 5 degrees. And the model also included a bit of turbulence to disperse the eels a bit. And also there was a salinity detection threshold. This was found to be quite important for getting the eels to be in the right location, and this defines the point below which they can't detect the salinity anymore, which appears from the modelling appears to be important. So they can't, once they can't detect this threshold anymore, they don't have a navigational cue to go by. There's a few other parameters in there which I won't go into. So what we did was run the simulation with various behaviours switched on and off. The first scenario, we had no STST behaviours switched on. So basically the eels just swam up the Thames following the salinity gradients, and that's all. That's all they did, was they swam up the Thames. But the rest of the scenarios, they had various things switched on and off, like swimming down and anchoring at the bed, anchoring during the daylight, which is eel behaviour, upward migration on the flood, so whether they swam towards the surface, edging during the slow ebb, so edging, like the edging behaviour, as I mentioned, and also whether they drifted or swam during the flood tide, just to check how much energy this saved. Right, I'll just animation again. So this is an animation of one of the model results. This is the one where they have all of the STST behaviours. Let's get that going. So eels in the model are swimming up the estuary. Just to point out, it's a long simulation, so I jumped 30 days in this and then plotted it for a few days. And as you can see, the yellow dots, which are the eels, tend to bunch up on this red contour. I don't know if you can see a red contour, which is that threshold in salinity. So once they reach this threshold, they don't really have a navigation cue to go by. And so they're bunching up at this high water point of that salinity threshold. And over time, I don't know if you saw that, basically you got more and more. And this is Brentford Creek where we're counting the eels. And you can see you end up getting a big concentration close to Brentford Creek. I'll just, in the next few slides, I can explain that a bit more, in a bit more detail. So in May, what happened was we had very few eels being measured. And the reason we think is because the salinity is low and the eels aren't making their way up the Thames, because the salinity, the point at which their salinity detection, they can detect salinity, is further downstream from Brentford. In July, this point is further upstream, and you start getting some numbers at Brentford. Sorry, these black, in this case, the eels are black dots here. So you can see quite a high concentration there. Now in September, early September, you get a big peak in measured numbers. And we think the reason for this is because this threshold in salinity is at high tide is roughly around Brentford. And so you end up with a big concentration of eels here. Later on in September, because there's been some less rainfall, the salinity has gone past Brentford, and you end up with the concentration of eel further upstream. So it'd be interesting to do a bit of more research, but it looks like this is the reason why you get a drop in numbers. So if we plot all of the scenarios together, this is all the numbers of eels in the model, and the black line is the number of measured eels over time, so for each of the scenarios. I'm not going to go through all of these graphs, but basically they all look fairly similar, but we're getting these peaks about the right time. That's the main point. The only scenario where we didn't get these peaks happening was in the scenario where the eels didn't swim down to the bed and anchor themselves. So they weren't performing any STST behaviours, so they weren't able to sort of keep up with where this high water mark in the threshold was, the salinity threshold was, so you weren't getting the defined peaks happening. If we then look at the relative energy expenditure, an interesting which is basically relative to no STST behaviors, so run 1, so that's 100% energy. We find that the most efficient behaviors are ones where they perform no deal behavior. But that's actually not a very realistic thing, because we know eel do actually perform this deal behavior. As soon as you include deal behavior, then the most efficient of all the scenarios was scenario 7, which just so happened to be the one where we included all of the STST behaviors. So that's a really important thing. It seems that if you include deal, you need all of these STST behaviors to be efficient at migrating up the Thames. Interestingly, the worst case in terms of energy efficiency was when we increased the swim speed. And the reason for this is the main limitation on the eels progressing up the Thames isn't how fast they can swim. It's this threshold in salinity, which limits how far up the Thames they can get before they lose their navigational cue. Anyway, that's some take-home messages for that case study. Right, now we'll lurch on into the Milford Haven Waterway, where we tested the entrainment of the eels in Pembroke Power Station. Milford Haven Waterway is part of the Glethau estuary in Wales. It's 27 kilometres long and it's 55 kilometres squared. It's fed by 5 rivers. I won't name them, but there's 5 rivers coming in. There's also a gas-fired power station, which is located here. I hope you can see my arrow, but it's on the it's on the junction between the Pembroke River and Milford Haven Waterway, and there's an intake in Pembroke River and an outfall which goes into Milford Haven Waterway. So what happens is you actually get some fresh water going in the intake, and you get warm fresh water coming out of the outfall. The model was actually provided to us by RWE Npower, and it includes temperature and salinity. It's a 15-day simulation, and it includes the cooling water intake and outfall. So in the model, what we did was we introduced 91,000 agents at the mouth as a single release at the start of the run, and we just let them go, see what happened, whether they made it to the rivers. So the agents were then counted in polygons, these red rectangles you can see in this figure on the right, and we counted how many made it to these different places, like Pembroke River and all the other rivers, and the outfall and the intake. Here's an animation. I think probably most of you have seen this animation. We've got the eels swimming up the estuary. The orange dots are the eels. And basically what happens is they perform the STST behaviors I've described. So they go down to the bed on the ebb tide. That's why they stop. You can see them actually doing this stopping on the ebb tide. And then on the flood, they rapidly get drifted upstream. And they quite rapidly, within a few days, a lot of them have already made it to the rivers. If you focus in on Pembroke Power Station, you can actually see quite a few of them are actually going into the intake. It's interesting that they sort of tend to, just a few of them go in just at the beginning of the ebb tide. And the reason for that is that there's some fresh water which goes into there, and it looks like it's actually, so you've got a bit of salinity coming in, but low salinity near the intake, and so the eels think it's the river. That's where the river is. And a similar thing going on at the outtake. You've got fresh water coming out, and so some of the eels think, aha, that's the river, and they swim towards that. So anyway, most of the eels by this stage have actually made it either to a river or gone to the intake. And I think that's, yeah. Just one other thing to notice in the model, quite a few do get trapped, but eventually, they tend to come out in big groups and make their way up en masse. So just the results from that model. Here's a time series of the eels in the different rectangles I said earlier. So the dark blue line at the bottom is the entrainment in the intake, and the lighter blue just above it is the entrainment actually in the outfall, which was, we weren't initially looking at the outfall, but we realized actually quite a few were swimming towards the outfall. Overall, the results suggest that 77% of these eels end up in the river, 2% have ended up in the intake, and nearly 5% have swum into the outfall, which was a bit of a surprising result. Yeah, so I think that's basically that model described. So to summarize, the key points from this talk: in the last few decades, European eel have become a critically endangered species. That's a fact. As well as other factors, power station cooling water intakes are a known problem, but the question is, how much of a problem are they for juvenile eels? To answer this question, we've developed an agent-based modelling of migration of eels with the aim to assessing the impacts of cooling intakes. The agents are able to navigate autonomously up the river using the salinity gradient and flow vectors. The new ABM shows good agreement with eel trap records in the Thames estuary. And in that test case, it's shown that by including these STST behaviours, it improves the efficiency of migration, but only if eel behaviour is also included. For the entrainment test case, the results suggested about 2% of eels migrating through the Milford Waterway get entrained in the intake, whereas more actually swam into the outfall, which was a bit of a surprise and needs further investigation to see if that's actually a problem or not. Finally, there is potential for this model to be used on other fish species, and so we're very, very open to applying more investigation of other species using this model. And that's it. Thank you very much for your attention.
Thanks very much, Tom. So we've got a few questions already in the Q&A, so I'll just go through those. But if you have any more, then please do put them in there. So we've got the first one is from Stephen Pattenden, who says, are the impingement estimates based on adult equivalent or absolute numbers?
They're absolute numbers. Sorry, of the eels, that's absolute numbers. Yeah.
Okay. And then we got the second one is from Mark Weber, who says, was the study with Delft 3D underlying also done with the Hydroboids Lagrangian tracking model?
Yes, it was. It was. We basically we can apply the model to pretty much any model you want, as long as because we can read, as long as we can read in the result file, we can apply it to any model.
Okay, and then we got one from Tom Scanlon, or two actually. He says, thanks for a fascinating talk. The first question that Tom's got is, would it be possible to have contaminant sources such as those from agricultural pesticides or other pollutants as a behavioural cue in the agent-based model?
Yeah, that's an interesting question, because in the model we've assumed that it's salinity. The thing is that's it's actually questionable whether that is actually the cue that they follow, or could it be something else in the fresh water that they're following? It could, in fact, be, as you say, it could be some odor or other chemical. And inside the fresh water, you can also introduce pollutants as well. We could introduce that, and I mean, you know, basically we could apply anything to this sort of technique, and that's the beauty of the modelling technique. You know, it's very adaptable for including this, you know, as you say, pesticides and things like this. So yes.
And then Tom's second question is, are the Hydroboids and Eel agent-based model codes available as open source?
At the moment, no, I'm afraid they're not, because we're we have invested a lot of time and expense into this. I am investigating it, but at the moment, I'm sorry, not at the moment.
And then we got Mark Weber again. He's saying, is the salinity, the low salinity in your studies also a proxy for the up-estuary substances, for example, decaying plant material?
Yeah, that's the I think that's what I mentioned already. By assuming they're swimming towards the fresh water, we're assuming they're swimming towards whatever is in the fresh water. So yes, it's a proxy for that.
Okay, and then Matt Golock's got another question, which is there a plan to do a model similar to the MWH model for the Thames that shows movement into tributaries?
I think that in the Thames it's tricky because it's a very much it's got a lot of locks and weirs, and so the tributaries are all kind of quite enclosed, and they act as barriers, and this is the whole problem of eel migration in a nutshell. So it's a little bit more tricky, that one. We do have additional data which from ZSL on the other tributaries like the Lee River, and actually also at Teddington, but we need to investigate those a bit more. So yeah, it would be nice to tie that in as well. Yes.
And then we got one from Chris Bell. He says, thanks for an interesting talk. He says, is there anything in the eel behaviour model inputs to represent behaviour towards eel residency in the estuarine or brackish zones, rather than a desire to move upstream / against the salient gradient?
That's a good question. It's true that eel are known to actually stay within the Thames. And to be honest with you, I'm not sure we have enough data to actually confirm that or not. But there are eel, some of the more adult eel are found in the Thames. So it's an interesting question that we should look at some point.
And then Mark Webber has another question, which is how easy would it be for hydrobiodes to be applied to other fish species? Oh
well, I mean it's very easy, to be honest. The only limitation is the data on the fish species, and that's the key thing. If you've got the data, it can be applied, and it's just coming up with that data. It's basically laboratory experiments on fish are needed for parameterization, and even better if you've got any in situ data, but that's very hard to come by. So data is all important.
And then there's a comment which you might want to respond to from Andrew Moores, which says swimming into the outfall may not be possible as velocities are too high, plus the system tends to have a weir that prevents full progress into the station.
Yeah, I totally agree, and this is basically what we need to do is go back and have a look at that. I'm just presenting what we found in the model, and it's an interesting point because the model shows things which you wouldn't expect, and then you can go back and you can collect data, and this is all about this sort of mixing up modeling, measurements, and a bit of imagination, and you can go and work out exactly what's going on. So yeah, we basically need more investigation in situ measurements and just to check what's going on.
I think that's everything, unless anyone else wants to put something in the chat. I mean, we've got a few minutes left. We've got 5 minutes essentially left. So if anyone has a question they want to put in the chat, we've still got a little bit of time for Tom to answer it. Oh, sorry, yeah, there's one from Tanya White. She says, very interesting talk. Could I please ask your thoughts on the next steps and how the research community are combining to work towards greater influence of the design and remediation / policy? I presume that's with regards to protecting eels and other marine species. Yeah,
I mean that's a very broad question. I'm not sure I can answer it. I mean, but from my very limited experience at HR Wallingford, in terms of dealing with a few clients, etc., I know this kind of approach is being used for environmental impact assessment on a more regular basis, and that's heartening to see that in the past things were done possibly a little bit less detail, but now with the advent of better computing power, we can it's gradually becoming more commonplace to look at things in this kind of detail.
Right, I think that's it in terms of questions. So we're pretty much on time. So unless any more questions pop up in the next 30 seconds or so, just to say, you know, that this webinar will be recorded, and provided that there's no hitches with the copyright, which I don't think there will be, then it will be available in the future on the SciWem website, on the YouTube page. So you can, you know, if you've got colleagues or people who haven't seen this, then you know, you can send them along to the SciWem web page or the YouTube site, and it should be there. So yeah, thank you very much, Tom. Just to finally sort of to draw to your attention to the other events, I know Barbara and Jane have put those in the chat and on the website. So I don't know if you want to say a few words, Barbara, just before we end.
Yes, I'd just like to thank Tom for a really, really interesting talk, and also for the Central Southern Branch for organising this event. It's very much appreciated. There are, if you want to see what the upcoming events are of other branches as well as Central Southern, and also the international events that we've got, then you can just go to the events page, and that is regularly updated, and you can log in there. Branch events do tend to be free, and there are also some international SciWem events that are free too. There are a couple that we actually do charge for. We've also been looking at a series of topics for our main webinars, and that one of those does include net zero. So again, we had a recent one yesterday on best adaptation reporting practices. So again, this will be available on the recording will be available shortly. So if you didn't get a chance to go to it, then that will be there with the other recordings. And I have put up the link on the chat. So thank you very much.
Thank you.
Thank you.